So just one more time, just so everyone's totally clear on this. If we have a function like on G here, where we have something that x cannot equal, x cannot be 1 in this case, again, what we want to do is we'll take and factor the numerator and denominator if necessary, okay? And we'll determine whether that value that x cannot be will give us a whole or an asymptote. In this case, it cancels out, so we have a whole at x equals 1. And now that it's canceled out, since it's a whole, we know the function will be approaching whatever that value is. It just doesn't happen to exist at that one point.
Sorry, the whole is what cancels?
Whole is what cancels. So it's at x equals 1, and now we're just doing the limit as x approaches 1 of x.
So then when you write it,
Oh, that's gross.
well, first of all, what's that?
What does that equal? 1. Okay, and what this looks like graphically is this is the line y equals x. Okay? But when we have this part in it for our original function, all that means is that we have this hole right in the middle of it. It's still a line y equals x, it just has a hole cut out of it.
So the whole is you take what cancels, and then you plug in what would make it undefined, and that's the whole.
Yeah.
So the whole isn't x minus 1, it's just 1 because that would make x minus 1 2.
The hole is at the point 1, and then we plug in 1 to what's left after we reduce to get the y coordinate. And in this case, that's
It
what.
doesn't matter if it's on the top or the
No,
bottom.
if it were on the bottom,
Oh, yeah.
yeah, it's just whatever is left is what you're going to plug it in. So, all right. Now, you've done some of these just kind of thinking through it logically and whatnot, and that's good. What we want to look at today are some actual theorems related to limits. And even though the IB exam doesn't necessarily test you directly on the limits very much, if at all, it is very important that you understand how limits work and also how these theorems that we're going to look at work in order to properly understand derivatives and integrals. Because remember, derivatives and integrals are both derived from the limit. Okay? So we've got to make sure we understand that before we move forward. Okay? So I want to look at some limit theorems, and a number of these are simply things that we've already observed, but I want to make sure that you see them formally. And then we're going to look at other ones that aren't quite as intuitive that'll help us moving forward. Okay? So here's a couple that are a little bit intuitive. First of all, an observation we made yesterday as we kind of introduced that is that if we have a common function, or if we have a polynomial, okay, then the limit will simply be that function evaluated at c. Okay? We already said if you have a polynomial, we know polynomials are defined over all real numbers, and we know they're continuous over all real numbers. Therefore, we can simply evaluate no matter what we're approaching. Okay? So that's one thing. A second one is the limit of a constant function. Okay? Okay? And to avoid confusion, I thought I switched this once already. There we go. If f of x is approaching some constant value b, then the limit as x approaches anything is just going to be the constant. The limit of a constant is the constant.
I don't understand, understand how to evaluate them, but like, what is a limit?
That we can talk about. That's what we spent a lot of yesterday going over. I know you were
I'll
here.
watch it.
We can talk. Then we have kind of the combination of these two ideas, and that is the limit of a constant multiple. Okay? This is one that you may or may not use a lot, but it can be helpful in certain cases. Okay? It can just make our life a little easier. When we have a function that's being multiplied by some constant value, in this case b, you can, essentially what you're doing is you can basically factor that b out or pull that b outside of the limit, take the limit of what's still in the limit, and then multiply that result by b. Okay? So, just as an example, let's say that I had the limit as x approached 7 of, let's say we had something like this. We had 4 pi x squared over 3. Actually, let's do x cubed. 4 pi x cubed over 3. If I wanted to find the limit of that, I know this is kind of a simple one, but what I could do is I could take all the constant multiple parts out, okay? Every constant that I'm multiplying by, which would be a 4 pi and a 1/3. So I could take that 4 pi over 3 out of the limit and simply find the limit as x approaches 7 of x cubed. Okay? And that would be, what, 343? 49 times 7, yeah, 343. Okay? So now I just have 4 pi over 3 times 343. Okay?
Is that just an example?
Yeah. It's just one example. Another one might be something like this. If I had,
Wait, can you go up a little bit?
yeah, it went too far. If I had the limit, let's stick with x equals 7, of some polynomial like this. Let's say I've got a 5x squared minus 15x plus 25. Okay, that's a polynomial, so I could just evaluate it straight away. Or if I saw that, hey, there's a common factor of 5 in there, I could take the 5 out and then just find the limit as x approaches 7 of x squared minus 3x plus 5. That would keep my numbers a little bit smaller.
And then you just multiply by 5.
And then I just multiply by 5 at the end. Yeah. So 7 squared is 49, minus 21 would be a 28, plus 5 would be 33. So I have 5 times 33, which would equal 165. Okay? So again, this is a way of just keeping our numbers a little smaller, rather than having to do 5 times 49 minus 15 times 7, you know, now the numbers are smaller. Okay, so that can be a handy one to use as well. Any questions so far? All right. Now, we'll get into some that may or may not be quite as intuitive. First here is the limit of a sum of a couple functions. Okay? The limit of a sum equals the sum of the limits of the individual functions. Okay? So here you see we could look at this as a polynomial function, x squared plus 3x. And then we have this rational part that also has a radical inside of it. Okay? And if we're finding the limit as x approaches 5 of this whole thing, we can find the limit as x approaches 5 of x squared plus 3x, and then add to that the limit as x approaches 5 of the square root of x over the square root of x minus 1.
So it's kind of like log functions or something.
No, because remember logs, if you had like multiple logs added together, then you would multiply the stuff that was inside. So that was a little bit different. Now, what benefit is there to this? Okay? Well, basically, before you get too far, you can look at this more complex part of it and determine whether this limit even exists. Okay? So you look closely at this, you see, okay, well, what's my domain for that part? What's the domain for this part right here? The
Except the square root of 1.
what?
Everything except the square root of 1.
Okay, x can't be 1.
Square root. Right. Or, no, 1, yeah.
Yeah. What else can't x be?
A negative number.
A negative number, okay? So x has to be greater than 0, and it cannot be 1. All right? So right off the bat, since I know that this 5 is not one of the values that's eliminated, I can go ahead and just evaluate for 5. All right? However, let's say this problem was this. Let's say the problem was the limit as x approaches negative 5. Okay? Here I could save myself some time by recognizing this limit right here is at a point where my function's not even defined. So what's the limit?
It doesn't exist.
It doesn't exist.
So then the whole thing doesn't exist.
So the whole thing doesn't exist. There's not just a hole at 5, okay? There's not just a hole at 5, but this part right here, the limit does not exist. Therefore, it doesn't matter what this part of it's approaching. Because something plus does not exist, all right? We can ignore this, save ourselves some time, and then we, just by looking at this as the sum of separate limits. Okay? That is a benefit of a number of the rest of the theorems that we're going to look at related to limits here. Okay, we're going to look at 1, 2, 3 more. And that's a side benefit of all of these. If you know one part of it, the limit doesn't exist, then you automatically know the limit of the whole thing will not exist. Okay? All right. So here's another one, the limit of a product. The limit of a product is the product of the limits. Okay, if you have two functions multiplied together, you do not have to FOIL these together and then find the limit of the polynomial. You can simply take the limit as x approaches 5 of the first factor, x squared plus 2, and then you can multiply that by the limit as x approaches 5 of x minus 7. Okay? As you get more and more comfortable with these, you'll do this same concept just in your head without writing the whole thing out. Okay? But you recognize this here, and you say, okay, well then that's 5 squared is 25 plus 2 is 27. And 5 minus 7 is a negative 2. So this has to equal a negative 54. And that's the same thing you would have gotten had you FOILed it together and then evaluated. Okay? Now, you might notice I have here the limit of a product, but down here we have a division problem.
So the problem
Okay.
is,
It's still a product because division is simply multiplying by the reciprocal of something, okay? So we could look at this as the limit as x approaches 5 of the x squared plus 2 times the limit as x approaches 5 of the square root of x plus 3. Again, here's something where you can save yourself some time by looking at this part. I know the domain, oh, that should be 1 over, sorry. Looking at the domain, it can't be negative 3. X cannot equal negative 3 because I'd be dividing by 0. And x can't be anything smaller than negative 3 because I'd be taking the square root of a negative number. So x has to be greater than negative 3. So right off the bat, if I look at it and I see x has to be greater than negative 3, but I'm approaching, say, a negative 5, that's out of my domain. Therefore, this doesn't have a limit, so the whole thing does not have a limit.
Why was the one that the reciprocal, why was that undefined?
No, I was saying if this were approaching negative 5.
But since it's
This is
not-
why you at least, you may not write it as separate parts like this. In fact, as you get more comfortable, you won't write it like this. But this is at least how you should be thinking of it. Think about them as two separate functions rather than just one big function. And if you isolate it and look at the one that has the potential to cause trouble, this one here, look at it. If that works, then you would have had to do that work anyways. So you haven't lost any time, but you could definitely save yourself some time.
But no, but there's no problems here, so we can just do it.
Yeah, there's no problems here, so we can just go ahead and evaluate. This would be 27 times 1 over the square root of 8. Okay? So here we go, 27 root 8 over 8. We rationalize it. So, we have the limit of a sum. We have the limit of a product. This, you can probably anticipate, introduces another rule. Because division is just multiplying by the reciprocal, and we know multiplication works, we automatically know that if we have division, okay, we can simply find the quotient of the limits as long as the denominator works. Okay? So we look here, x plus 2 is continuous, x cannot equal a negative 2, but we're approaching 3, so that's okay. So now I can take the limit of the top, 9 plus 6 minus 5 is 10, and I can divide that by the limit of the bottom. 3 and 2 is 5. I just divide those two, and the limit of the whole thing is 2.
How did you get the 10? Oh, because you plugged the 3 in.
Yeah, we just plug the 3 in.
And how
We're-
is it a special rule that that's what you do anyway?
Well, the key here is you can just take, all I did was, I noticed, hey, this is a polynomial, so I can take the limit by simply evaluating.
You can do that with a lot too.
Well, I looked at this, yeah, this is a line, and as long as we're not approaching -2, that's going to be okay. So as long as the limit of my denominator does not equal 0, all right, then I can just find the limit of the top, the limit of the bottom, and divide. Okay, I don't have to try to simplify this algebraically. Okay? But what happens if the denominator does equal 0? This takes us back to where we started today. What do I do if the denominator would equal 0, like in this case?
Or just an asymptote.
Yes. Is it a whole or is it an asymptote? And that's what you've got to find out. All right? So how could we go about finding this one? Is this a whole or an asymptote?
Nothing cancels.
Can we make something cancel?
What could you do? X plus 6x minus. But it's square root.
Well, hang on. What? Square the numerator and denominator? We can't square it. We can do something, but well, here's the thing. If we plug in 36, I get 36 minus 36, which is 0 on the top. And that's actually okay. It's okay to have 0 on the top. But I have the square root of 36 minus 6. That's 6 minus 6, that's 0. That's what we call an indeterminate form. You got 0 over 0.
So is the
Okay. Well, that's what we have to figure out. All right? My domain here is that x cannot be 36. It also can't be a negative number. Okay? X has to be greater than 0, and it can't be 36. Okay? So you have two options basically. Watch this. You have two options. One is a little bit more kind of related to something you've done before, and that is try rationalizing the denominator. How would we rationalize the denominator? There we go, the complex conjugate. And this is kind of what I said. You can't square the top and the bottom, but we can multiply the top and the bottom by the same thing. The square root of x plus 6 and the square root of x plus 6. Now, what do I get in the denominator when I multiply those? Yeah. Check this out. Now, what happens? Yeah, we got a hole. We've dug ourselves a hole. So now, we can cancel that out. We have the limit as x approaches 36 of the square root of x plus 6. Yeah, so 12. And this function actually has a hole at 3612. Okay? So, if you're not sure if it's a hole or not, and by the way, if it were like x minus 52 or something, and you say, okay, there's no way a 6 is going to match up with a 52, you could probably assume that that's going to be an asymptote, right? But in this case, you see the 36 and you see the square root of x minus 6, you see there's at least a possibility that they're related and something could cancel. So you need to examine it further. The other way you could do this one, though, if you think about this, and this is kind of what you were saying, Samantha, this does not factor into x plus 6, x minus 6. However, just because they aren't perfect squares doesn't mean we can't use that idea. We can factor this into conjugates. It's just, since we had an x to the first to start out with, we'd have a square root of x plus 6 and a square root of x minus 6. You can actually do difference of squares no matter what you have. Okay? It's just in Algebra 1 you learn how to do it with squares. Okay? But you actually can expand that same idea, and then you see square root of x minus 6 will cancel, and you're left again with the square root of x plus 6. Okay? However you get there, just get there. But that's one thing you can do. All right? Any questions about that? Okay. Finally, we have the limit of a power. Okay? The limit of a power. And what we're talking about is when we have a function that's being raised to a power. And again, this is one that you could figure out without using this theorem, but it does make things a little simpler. All right? For example, if I had the limit as x approaches 5 of x squared minus 21 cubed, and we didn't have anything but the rules that we've already looked at, I'd have to do this one of two ways. I'd have to either FOIL this all out, okay, or I'd have to write it out 3 times and use the product rule. Okay? I just use the same one for all of them. But this one, using the rule that we have here, my function is the x squared minus 21. And rather than cube it first, then take the limit, what this theorem says is, I could take the limit as x approaches 5 of just the x squared minus 21, figure out what that equals, and then cube it. What? Yeah. Now we just evaluate this, and that's 4. The 4 is what's in the brackets. 4 cubed is 64. Okay? Close. And you see here again, it's a little simpler, quite a bit simpler than foiling the whole thing out or even writing it out 3 times. Okay? So, those are our 3, or not 3, more than 3, 3, 4, 5, 6, 7, are 7 limit theorems. Okay? So,